Hey everybody, welcome to today's video, which is about chemical bonding. So, there is a misconception about bonds between atoms. There's a tendency for us to think of this bond as a physical thing, a stick, a string, a spring. It is not anything physical. It is simply the Coulombic attraction between the positive charge on one atom or ion and the negative charge on another. So let's take a look at these two very simple atoms with protons in the nucleus. And, we've talked a lot about the Coulombic attraction between an atom's protons and its own electrons. And that Coulombic attraction holds the atom together and gives it its shape and its size. It defines its radius, actually. But there is also Coulombic attraction between the protons of this atom and the neighbor's electrons. That is known as electronegativity, attraction of an atom for electrons of a neighboring atom. So I'm just going to represent that these protons are attracted to these electrons as the electrons are attracted to the protons next door. And same thing here, Coulombic attraction between protons of one atom and electrons of another. Now, if that attractive force is strong enough, then we say the two atoms are bonded. But there is also a force of repulsion going on. So there is a limit to how close these two atoms can get to each other. At some point, if they're too close, the protons will repel each other, as will the electrons in the two atoms, push away or repel. So next, let's consider this bond energy curve. Take a moment to orient yourself to what it's showing us. The x-axis is labeled distance between nuclei, and that's in nanometers. And the y-axis shows potential energy. And the potential energy is 0, right here in the middle. Above that, the potential energies are high, denoted with positive numbers, and below, potential energy is very low with negative numbers. So let's start out here at the far right, where we are showing the two atoms and their nuclei being very far apart, 20 nanometers, 30 nanometers. Okay, in those instances, the distance is so large that potential energy between them is 0. And there is no repulsion, and there is no attraction. So in that case, with the atoms so far apart, potential energy between them is 0. All right, now let's bring the two atoms very, very close. Right about here, I'd say that's about 3 nanometers apart. The potential energy is very, very high. When that's the case, we have very strong repulsion. Okay, those atoms are not happy at that very close distance. And the protons are repelling each other, and the electrons of the two atoms are repelling. But if we bring them slowly farther and farther apart, we see that the potential energy reaches its lowest value at a distance of, I'm going to say that's about 6 nanometers. So for the two atoms that are being depicted here, that's the optimal distance between the nuclei. And we say that when the potential energy is the lowest, that's when the attractive force is the strongest. Let me get this zoomed out a little bit. So we are looking for the potential energy at its lowest. We're looking for the dip in this potential energy curve. And when the attractive force between atoms is strongest, then we find the potential energy is the lowest. And that is where the chemical bond is optimized. Okay, now We're going to consider three different types of chemical bonds. I want to mention briefly metallic bonds between metal atoms. We're going to talk much more about that kind of bond in a later unit. So let's just sort of table that one for now. And let's put our focus on these two types of bonds, which you're familiar with from first-year chemistry: ionic bonds and covalent bonds. And the difference in the two is really about what we find for the electronegativities of the two atoms in the bond. When the electronegativities of those two atoms are very different, that means that one atom is particularly greedy and the other one is very generous. And in that case, an electron is going to be transferred. So this atom has the very high electronegativity, and this one has a very low electronegativity, and the electron ends up being transferred to this atom. That means, of course, that this is no longer an atom, but because it has one more electron than it has protons, it's what we call a negative anion. And the atom over here, which gave away an electron and now has a surplus of protons, is the positive cation. The electron density is over here. Or we can have two atoms whose electronegativities are fairly similar. So perhaps they're both greedy for the electrons, but we don't have one markedly more greedy than the other. So we're not going to end up with a transfer or a giving away of electrons. Instead, they end up sharing the electrons, and the electron density is focused in between them. Electron density is between the two nuclei. All right, remember in an earlier unit when we talked about trends on the periodic table, and in particular we said that going across a period the atoms are getting smaller, and also the smaller sizes were up at the top. Okay, so now I'm going to add electronegativity trend to this graphic. I have highlighted in blue the electronegativities of these four atoms, and I'd like you to do the same. Remember, electronegativity, you can kind of think of it as greediness. It's the attraction of an atom for shared electrons, for electrons of the neighbor. This trend is going to follow Coulomb's law. No big surprise there. So you remember that Coulomb's law told us that force of attraction, and previously we've talked about that being between protons and the electrons of the same atom. Well, it can also refer to force of attraction between protons and the neighbor's electrons. That force of attraction gets stronger when charge is larger. And look, as we go across this period, remember how nuclear charge got larger? So force of attraction is also going to increase. And remember, Coulomb's law also tells us force of attraction gets weaker when distance is longer, or let's flip it, gets strong when the distance is short. So just think about fluorine for a minute, tiny little fluorine atom. Because its protons are going to be a very short distance to the neighbor's electrons, just because he's so tiny, that short distance helps the force of attraction to be strong. Okay, so this electronegativity trend, which increases as we go up and to the right, culminating in fluorine being the very most electronegative, oxygen second most, and nitrogen and chlorine tied for third place. That's the trend I would like you to remember. All right, now lastly, let's focus on this idea of polarity of bonds. Let me make this a little bit bigger. Okay, so if, as we compare the electronegativities of the two atoms in a bond, if those electronegativities are very different, in other words, Delta En, that means change in electronegativities or the difference between them. If the difference between the two is equal to or larger than 1.9, that's an indication that the electron gets stolen by the more greedy or transferred over to the more electronegative. And that process results in a cation and an anion and an ionic bond. Let's look for just a minute at an example. Here is sodium with 11 protons and 11 electrons, and chlorine with 17 protons and 17 electrons. Now, you have this worksheet, which gives a condensed table of electronegativities, and again, I've highlighted the super greedy ones. Here we have chlorine, electronegativity 3.0, and we have sodium, electronegativity 0.9. The difference between those two electronegativities, 3.0, 0.9, is 2.1. So that's definitely a difference greater than this cutoff value. The electronegativity of chlorine is so great that it's going to flat out capture this electron and claim it as its own. So now I have, the pieces are not cooperating. So now I have 17 protons, but 18 electrons. So of course I've formed a chloride anion. And over here, sodium still has 11 protons, but now it's just down to 10 electrons. It has a surplus by 1 of 1 proton. So cation and anion are coulombically attracted to each other, and that attraction is the ionic bond. We learned in first-year chemistry to simply look for a metal bonding with a non-metal. All right, now let's consider if the electronegativities are different, but the difference is not quite as great. Let's say the difference is going to be somewhere between 0.4 and 1.9. In that range, there's not going to be an outright takeover of the electrons. Instead, the electrons are going to be shared, so covalent bond, but not shared equally. The sharing is definitely going to be skewed toward one end, skewed toward the more electronegative atom. So we use this notation sometimes on top of a bond to point to the more electronegative atom in the bond, and then we put a plus sign toward the less electronegative atom in the bond. So the bond is polar. It's lopsided. It has a almost negative side and almost positive side. But we don't want to ever flat out label the bond negative and positive, because that would indicate ions. Instead, these bonds are sharing bonds with some lopsidedness or polarity. Now here are some examples. I'd like you to write those down. In each case, the difference in electronegativities is in this range. So oxygen to hydrogen, 3.5, 2.1. That's a difference of 1.4. Okay, that falls in our range. Nitrogen to hydrogen. Nitrogen is 3.0, hydrogen is 2.1. That's a difference of 0.9. Again, it falls in this range. Carbon to oxygen. Now, whether that is a single bond between them or a double bond, the difference in electronegativities is still 2.5 minus 3.5, a difference of 1.0. It falls within this range. Okay, now, you won't always have a table like this to refer to, and in fact, chances are on the AP exam, you won't have this table. But what I want you to do is simply watch out for these 4. If one member of the bond is FON or CL, Fonkel, If one member of the bond is one of these, and the other member of the bond is not one of these, you can be certain it's a polar covalent bond. All right, and then next, let's suppose that the electronegativities are both high, but they're the same high number, or they're almost the same. In other words, the difference between them is very, very small, equal to or less than 0.4. Well, in that case, the electron density is evenly shared, and it's a sharing bond, covalent bond, that we label non-polar. We're not going to give it this notation. Instead, we just say, no, the electron pair that's being shared is shared right in between them, and the electron density is not skewed toward one of the members. Now, clearly, if the two atoms are the same, their electronegativities are the same, and the difference is 0. So this bond, nonpolar, covalent. Or this bond, nonpolar, covalent. Or this bond, nonpolar, covalent. Also, I want you to remember the carbon to hydrogen bond. The electronegativity of carbon and hydrogen, they are different, but the difference is only 0.4. That difference is so slight that this bond is essentially nonpolar. That's going to be very important in our next unit, so remember that one. And carbon and sulfur have the same electronegativities, even though they're different atoms. Another nonpolar covalent bond. Lastly, if the electronegativities both happen to be low, and they're the same low number or very close, that is an indication of a metallic bond. And again, we'll be talking about those in more detail in a later unit. Okay, now to wrap up, you have some practice down here in which you're given a substance and you're contemplating the bond between the two elements, iodine and chlorine. They've given you the electronegativities of the two atoms. Or if you didn't have those, you could always find them from this chart. Okay, so you consider the difference between the electronegativities, and then based on that difference, indicate what is the type of bonding. Is it ionic? Is it a sharing bond that's lopsided, polar, covalent? Is it a sharing bond that is pretty even, non-polar, or is it metallic? Okay, guys, I hope that was helpful.